computer find the shortest path in a massive, chaotic network. Whether it's navigating a complex maze or finding a mutual friend in a global social network, the secret to untangling this chaos is a fundamental algorithm known as breadth first search, or BFS. By exploring level by level, BFS guarantees the most direct route. Let's master how it works. So, what exactly is breadth first search, or BFS? At its core, it is a fundamental algorithm used to traverse or search through graph data structures. Unlike other methods that dive deep into a single path, BFS takes a wide approach. It explores all immediate neighbors of a node before moving to the next level. This layered exploration strategy guarantees something incredibly powerful. It will always find the shortest path in any unweighted graph. The engine driving the systematic search is a data structure called a queue. It operates on a strict first-in, first-out, or FIFO principle. Nodes discovered first are explored first, ensuring the algorithm expands evenly and predictably across the entire network. To understand the heart of breadth first search, we need to look at its core engine, the first-in, first-out, or FIFO queue. Let's break down the algorithm into 3 simple, repeating steps. Step 1, we start by taking our initial node and adding it to the queue. It is now discovered. Step 2, we dequeue or remove the front node from the queue and mark it as fully visited. It has now been processed. Step 3, we look at all the unvisited neighbors of that node and immediately enqueue them. They are waiting in line for their turn. This cycle repeats: dequeue the front, visit it, and enqueue its unvisited neighbors. This guarantees we explore layer by layer. Let's walk through a concrete example. We have a graph with nodes A through F, and we want to traverse it using breadth first search. We start at level 0 with our source node A. We mark A as visited and add its unvisited neighbors B and C to our queue. Moving to level 1, the queue gives us node B first. We visit B and discover its neighbors D and E, adding them to the queue. Next in the queue is node C. We visit C and find its neighbor F. Notice how we finish level 1 entirely before touching level 2. Finally, we process level 2, nodes D, E, and F. Because we use the first-in, first-out queue, the frontier expands evenly, guaranteeing the shortest path. Now, let's translate the visual logic of breadth first search into actual code. We start by initializing a queue to keep track of nodes to explore and a set to remember the nodes we've already visited. Next, we enqueue our starting node and mark it as visited. This establishes our foundation. The heart of BFS is the while loop. As long as our queue is not empty, the search continues. Inside the loop, we dequeue the first node. This becomes our current focus for exploration. We then look at all its unvisited neighbors. If a neighbor hasn't been visited, we mark it as visited and push it into the queue. This guarantees we explore layer by layer, never processing the same node twice. While pseudocode gives us the mechanics, BFS is the hidden engine powering many technologies we use daily. On platforms like LinkedIn, finding your 2 ND-degree connections is a classic BFS level-by-level traversal. For GPS and mapping apps, BFS guarantees finding the absolute shortest path across unweighted road networks. Search engines also rely on BFS web crawlers to systematically index the internet, moving link by link. Now let's analyze the performance of breadth first search. The time complexity is big O of V plus E. Why? In the worst case, BFS visits every single vertex, V, exactly once when it enters the queue. And it explores every single edge, E, to check for unvisited neighbors. Hence, time is proportional to vertices plus edges. For space complexity, it's big O of V. The queue must hold all nodes in the widest level of the graph.